Welcome back to the ChemDoctor, and this is the third video on the playlist on naming ionic compounds. In the first two videos, what I did was I defined the elemental ions and emphasized the fact that there are fixed known charges for group 1A cations and group 2A cations, and we talked about the transition metals and the fact that they have variable charges or variable oxidation states. The primary model system there was iron, where it can be iron plus 2 and iron plus 3, and therefore when naming those cations we utilize a Roman numeral to indicate the charge on the cation, whereas for the group 1As and 2As we simply need to name the cation using the neutral name followed by the word ion. Alright, so now, and then I also introduced the molecular ions or the polyanions. So now what we're going to do is actually start to put this to practice. And there are two main categories in terms of naming. We have the type 1 binary ionics and the type 2 binary ionics. The word binary just simply means that we're dealing with two different types of ions, a unique cation and a unique anion. Now, for the type 1 binary ionics, these involve the 1A and the 2A cations. So we're dealing with the metal cations that have fixed charges on them when they are combined with either a 5A, 6A, 7A anion or a polyanion. In the case of type 1s, the name is fairly straightforward. We simply used the name of the cation that comes from the name of the neutral element followed by the name of the anion. So in the case of something like 5A, and if it was the nitrogen derivative, then we would call that nitride, for example. The type 2 binaries involve the metal cations that are transition metals, and since those have since those metals can have different charges on them, then the name will include the Roman numeral so that we know the charge on the cation depending on what anion it is combined with. So the whole name will involve the name of the cation, which is the name of the neutral element, followed by a Roman numeral that will tell us what charge is on that cation, and then the name of the respected anion, whatever that happens to be. So let's go ahead and just begin. And I'm going to start by taking us through some type 1 examples. Alright, so let's say we want to name this compound. Alright, Mg3N2. So this is magnesium nitride. Alright, so we use the name of magnesium as it would be in its neutral form. So magnesium, because it comes from group 2A and it has a fixed charge, we don't need, in the terms of the name of the compound, we don't need to include the ion as a name. But now, following the cation, we need the name of the anion, and in this case it's out of group 5A. We recognize that it's nitride. So this would be the correct name for this compound. Alright, now let's try another example where we go from the formula to the name. Alright, like in the last example. So in this case we see that that lithium is the cation. So we write down the word lithium, and that will be followed by the name of the anion, which in this case is out of group 6A. Normally the neutral element is sulfur, but because it's actually S-2 in this condition, then this will be lithium sulfide. Alright, now let's try a translation going in the other direction. So in this case we're going to have a compound whose name is barium chloride. All right, and we recognize that barium is out of group 2, so I write down its symbol first along with its charge. It's out of group 2A. The group number gives us the charge on it. And then we have chloride, which is out of group 7, and we have memorized that this is Cl-1. Now we need to combine this into a compound. So how do we do that? All right. Now, if you're in an advanced course like university level general chemistry, then you really need to understand charge balance. And what I mean by that is that you need to understand that when an ionic compound forms, the formula will involve the lowest whole number ratio of the ions that sum together to make 0. So you see on the barium we've got a +2 charge, and on the chloride it's -1. So in order to add these two things together and get a sum of 0, we're going to need 2 Cl minuses. So the proper formula is going to be BaCl with a subscript 2, like that. The 2 in this case emphasizes that there are 2 Cl minuses combined with the Ba plus 2. Now, if you have trouble seeing that, and like I said, if you're in an advanced course, you pretty much need to understand how the charge balance works. But if you're having difficulty with this, then there is a trick you can use that's called drop charge, where we take the magnitude of the charge and we move it down to the neighboring element in subscript form. So we would take the 1 from -1, and we would move that down in front of the barium here, just to the right of it. We take the 2 for the charge on the barium, we move that down for the Cl. And we end up at exactly the same formula. While this may simplify life for you right now, I'm going to tell you out of the gate that you must learn the charge balance issue if you want to survive general chemistry with a really good grade at the university level. The idea being is that when you finally end up with your chemical formula in the case of an ionic compound, you have the lowest whole number ratio of each of the respective elements, and the sum total of the ions must equal 0. This compound has no net charge on it. The net charge is equal to 0. All right? Let's try another one. So in this case, we'll translate potassium phosphate. Now, this is going to emphasize another issue, and that is that you must have the polyanions memorized, because otherwise there's not going to be any way for you to translate this. So phosphate is PO4 -3, and potassium is out of group 1 and has a charge of +1 on it. So now I compare my two ions. We have the polyanion phosphate with a -3 charge and potassium with a +1 charge. Therefore, it's going to take 3 potassiums to cancel the -3 charge that's on the phosphate. So the formula for this is going to be K subscript 3 PO4. All right, again, you can make the drop charge method work here. However, it's not what I recommend if you're in that advanced level class. So I'm going to circle the 3, and I'm going to bring it down into the subscript position on the K. I'm going to circle the 1 and bring it down over here in the subscript position on the PO4. End result, we get the same formula. All right. Now let's try our hand at a few of the transition metal ones. So let's start out by translating to the formula for copper 1 chloride. Now, the first thing to do is, like in the other problems, is to get our ions. So copper is going to be copper 1. So that's Cu plus 1. And chloride is out of group 7. So we've memorized that, and we know it's Cl minus 1. charge balance. We see that both of these ions have the same in magnitude but opposite charges. Therefore, they're going to come directly together to form their compound. So the correct compound would be CuCl. Drop charge. We put the ones in and we drop them, and you see we end up with the same compound. Okay? Now, let's try translating from formula to the name on this. So here's SNO. Now, SN is tin. O is oxide. Now, how do we figure this out? Because the tin is a transition metal. Therefore, we don't know its charge. But we do know oxide. It's out of group 6A. And we know that it's O minus 2. Now we inspect the compound formula that it's in, and we see that the subscripts for both the tin and the oxygen are 1. This is SNO. So therefore the tin has to carry the same in magnitude charge, or the same magnitude but opposite in charge. So the tin, it needs to be +2 in this case, since the tin and oxygen were combined directly to equal the formula that has a net charge of 0 on it. So now to get the name, we write tin, and then the parentheses that will hold a Roman numeral for the magnitude of this charge. So it's going to be Roman numeral 2. And then followed by the name of O minus 2, which is oxide. So the name of this compound is tin 2 oxide. All right, now let's try another one, but we'll translate the opposite direction. So we'll go, for this one, we're going to have iron 3 hydroxide. Iron 3 hydroxide. Now, the iron 3, that translates into Fe plus 3. The hydroxide, it's one of your 23, 24 polyanions. It's OH minus 1 because you've got it memorized. Charge balance. We see that the iron is +3. The hydroxide is -1. So you're going to need a total of 3 hydroxides to cancel all +3 charges of the iron. So the formula here is going to be Fe. Now, this is a polyanion, and we're going to need a subscript of a 3. So what we're going to do is use a parentheses, and inside the parentheses we put the hydroxide. Outside the parentheses we put the 3. So this is iron 3 hydroxide. If we didn't use the parentheses, here's what would happen. Some of you are going to make this mistake. You're going to write Fe, and then you're going to put OH, and then you're going to put your 3. So all of us have had parents that have told us, say what you mean and mean what you say. And I'm going to tell you right now, this is not what you mean. And you've said the wrong thing. Because this molecule, the way you've drawn it, is actually this. So if I translate this out, you've got H3O plus here. That's what this thing is, written in reverse. And this is just completely wrong. It's completely wrong. So you have to watch out for your polyanions, which are going to have subscripts. The polyanion must go inside a parentheses, and the subscript goes outside it. This way here, anyone who sees this understands that in this compound there are 3 unique OH minus molecules. All right, and with that I'm going to go ahead and close the video.